Hello. Um, sorry. Thanks for the introduction, Barbara. I hope everybody can see the screen here. And okay, so as Barbara mentioned, today's topic is about density fingerprinting of alloys, and this is me chanting .org. And this is my research group that I've been working with my family. And let me first introduce everybody to my family. Here at the very right, that's me. Then my sister, from right to left, Bharti Rathore, then my mother, Dr. Neem Rathore, and my father, Dr. Bhuvan Chand Rathore, and then my other sister, Pratibha Rathore. And we have been working on this project for quite a long time. As you can see, we started in 1999, the year I was born. Unfortunately, we lost my mother at the start of the pandemic. She has been a very big contributor to this project, and we really miss her. And yeah, if she was here, she'd be very proud. So, for our topic here, when we talk about alloys, well, in India, where I come from, we have gold, and we invest in gold in place of money. So the hardest challenge that we have with gold items is to figure out its purity of gold, because the cost depends directly on how much gold there is. And we have found cases, like as mentioned on the top left corner, where there's tungsten inside the gold bars. And this is a big problem. Like, big banks rely on this gold in exchange for money. So if this gold is impure, we have a major crisis coming in. And to talk a little bit more about this, well, we need to take a step back. This is a major problem here. We're talking about matter and itself. So we have a universe that has matter and energy, two constituents of the universe, in which matter can be classified as living and non-living, right? With living matter, we have the plant kingdom and animal kingdom. And the way we identify these creatures out here, us in them, is using genome sequencing and DNA fingerprinting. That's how we can tell who's who and who is related to who, so on and so forth. But then for non-living, we have two analyses. For non-living, we are talking about elements, mixtures, and compounds, and in mixtures in particular, which is alloy. We have two identification techniques. One is physical, and the other one is chemical analysis. So this identification is what our prime focus on. So as we talk, the identification, we have for non-living matter, we have chemical and physical. So in chemical, we can detect the constituents as well as the percent composition for whatever material is present inside of this substance that you have. The problem with that is you have to have a particular sample size, and at the end of the day, that sample is going to be destroyed. And that's a big problem. Also, it's costly. When you think about it, you need skilled workers, you need a lab to conduct these experiments, to, at the end of the day, figure out what was in that material that you had, which is now destroyed. This is not feasible for archaeologists, and when they find gold artifacts, they cannot do chemical analysis on it to figure out what's the percent composition. On the other hand, we have physical analysis, in which we have XRF, which is the radiation-based identification, where it uses the radiation to figure out the percent composition. And here we have surface analysis, so it only penetrates 50 microns deep and no more than that. And you can only do surface analysis, you don't know what's actually inside. Kind of like in the tungsten inside the gold bar case. You cannot figure that out here. The other method is the density-based analysis, which is what Archimedes used way back in the day. I'll get into that in a little bit. So here, Archimedes' method is a little bit limited to binary elements only. So, as I mentioned, Archimedes, the purity of gold, this problem arose way back in 240 BC, when King Herod wanted to figure out how much gold is in his crown. And so Archimedes worked on this project, and he figured out that that the density is the sole property with which he can figure out what % composition gold is in the crown. And how he did it is pretty amazing. So here, he's talking about density here. And what he found is, as he went into the bathtub, we all know the famous story, he went into the bathtub and the water level rose. That way we can figure out the volume. That is one property of matter. And the second is the mass, which can be measured using weighing. And with those things, those two things, mass and volume, we have density. Now, here, when he did the experiment and he found out that the density of the crown was not equal to the density of pure gold, that was indicative of the crown not being pure gold. This was the very first technique of identification or estimating the purity of gold. So to go a little bit deeper into this, how he calculated in my head. So this is the ratio of mass and volume. We get a very simple equation out here, slightly complicated, but it's actually very simple. So for two metals, we get M1, M2, two equations, and then two variables. So in mathematics terms, this is the easiest problem to solve. This is a determined system. And here's an example. As you can see, you can figure out how much gold and how much silver is in this particular piece of metal. Now, what happens when we introduce the third metal? You see the equation of top. There is a third metal M3 in there. And with that, there comes a major challenge. Now we have three variables and two equations. This is a classic underdetermined system of equations, where we have more variables than equation, and this cannot be solved. This produces infinitely many possibilities, what we call them probabilities, or in this case, we're calling them probable isodensity compositions, because they will always produce the same density, and they're all probabilities that can be proved. M3 could be 0, M2 could be 1, who knows? So solving this becomes a very, very difficult challenge, and this is where Archimedes' density method fails. So let's recap a little bit. Why did the Archimedes density method fail? Well, it's an underdetermined system. So many PICs are going to produce probable isodensity compositions, and out of those infinitely many compositions, how would we possibly identify which one is the correct one? That's a big problem. Many people worked on this, and the best solution we have had so far is a sparse solution, in which we are still having a hard time, where there's so much computation that it would take years to compute just one composition. So this is a big, big problem, and it becomes a non-polynomial time problem. So the challenges that lie ahead of us when you're trying to solve them, underdetermined is one. Then second is containing this infinitely many possible solutions into countable, finite compositions. Can we do? That's the second challenge that we have. The third challenge is, from this list of finite compositions, how do we find out which one is the correct one? That's the third challenge. And finally, can we do this in such a manner that our computation is not so excessive like it was in the sparse solution, that we can actually do it in real time? That's the third problem. So now, what we did. All right, so the same density equation that we had previously, we modified it. We said, okay, third metal, we're just going to write everything in terms of the third metal, and so on and so forth. So this is the equations we got. We got, again, two equations and number of variables, right? And then here we said, okay, what we're going to do is, instead of taking mass in grams, we are going to convert all of that into percentage. That would make it easier for us to contain it and say it would go from 0 to 100, no less than 0, no more than 100. Okay, so we converted into percents. And then after that, we discretized it by the way of imaginary numbers. We thought, okay, we're going to put a random number for the third metal, and that number will have to lie between 0 to 100 because it's a percentage. So with that, we supplied these values. We said, okay, put in 0, put in 1, so on and so forth. And we developed a software in which it supplies these values and it computes all these compositions. And we get a series of all these compositions. So this is one series. One thing to note here, I will show you in this is, okay. So here, 3 metals. I have a density that I put in, and I'm going to supply values from 0 to 100 with a difference of 1. That's our degree of difference. That's why we're discretizing it. And when you calculate this, so the software goes through all the iterations possible. It computes all of them using that equation. And when it computes, it creates one series. Important thing to note is within this series, so right here on the left of the screen that you see, that series has so many compositions, but most importantly, the actual composition also exists in the series. That was our way of hope. We were like, okay, the answer we need is in the series. So now we need to figure out how to identify this one answer. And for that, we worked hard. It took us 5 years to figure out what we need to do. And what happened is we accidentally found another series, another way of creating compositions. In the second list, which is created just like the first one, but equation is a little bit different. In this, we get the same actual composition once again within the list. And all the other compositions are completely different from the first list. So now we have only one composition that is common between these two series. So we called one series as normal, the other one as reverse, and we filtered out the common composition, which happened to be the actual composition. And this was our eureka moment. As you can see in here, on the left, this is forward, and on the left is normal, and on the right is the reverse series. And you can see in black and red, these compositions are the only common compositions between these two. Okay. All right. So we developed this method. We got our findings, and we published these findings in 2006. And if you want to read a little bit more into this, go to the website. Well, after this, we had so many questions left. We were like, okay, we found a second list of compositions. First question is, are these the only compositions that are left, or are we missing something here? Are there more? Who knows? So that is our first question. Second is whether each density, are there only 2 lists of these probable isodensity compositions? And does each list contain this actual composition? Is it like we find a third one and it doesn't appear there? Is that the case? So these were the questions we had. So we tried to find out how many possible series are there for a given metal program. And from there, we found out this wonderful formula of NC2, where N is the number of variables, in this case, number of metals to be calculated, and 2 is the number of equations we have. And when you solve this, you would get for each metal system, if you're solving for 3, 4, 5, 6, so on and so forth, you would get so many series, and it would not go beyond this. Okay, so now within here, in 3 metal, we would get a total of 3 series in total. So here you can see this is series 2, and I can switch to series 3 here, and this is the third list. And here you can see the actual composition exists again. Now, after this, we tried to visualize this data, and we plotted this in a ternary plot. 3 metals, ternary, 3 variables, X, Y, Z. And you can see all the compositions are aligned in a very straight line. This is what we're calling the iso-pycnic region, where all the densities along this line are the same. And you can see when I switch off all the other series. So this is series 1, and you can see all the compositions in those lists are like uniformly distributed along that line as a picnic line. And this is also the case with other series as well. But when you overlap these two, then you see there is one composition where both points superimpose. This is the point of merger. This is where there's the highest probability of finding a composition in here. So this is also the Vernier coincidence. If you think about it in Vernier scale, if you have ever had the calipers to deal with, you have 2 scales and you match which 2 lines of the 2 scales match properly. It's happening here as well, but it's happening in 3 different series altogether at the same time. So there's the Vernier coincidence happening here. And then okay. So I mentioned that the 3 similarly, you would get some 4 metal system. 1 dimension increases, and you have similar situation there. You get a plane. And here, that line that I mentioned with the iso-pycnic region, it also is the alloy space where for that particular density, all the alloys that are possible will be on that line. Same thing in the tetrahedron, where all the compositions for 4 dimensions for that particular density is going to be there. And you can see this here in green. This represents all the possible compositions for those 3 metals or those 4 metals that can be thought of or that can exist here. In this triangle and on this tetrahedron, and you can see where each kind of alloy would be present. So here, with this iso-pycnic region in 3 metals, we put a probability distribution where we said what is the probability of finding a composition in that iso-pycnic region. And we got a very interesting graph here. This is akin to wave interference pattern. And you can see the highest probability is again the actual composition, and you can see it's symmetric along this line, this vertical line. The same thing we found for 4 metal system. Looks a bit scary, pointy, but the highest peak is the highest probability. Okay, so if you think about it, the density is acting like a genetic code. Just with that number, they're able to figure out what constituents are there. It tells us all the details. It's kind of like the DNA. So if you think about it, it's kind of like the number of chromosomes an organism has is similar to the NC2 formula that we had that tells us how many series are going to be there. Same thing here. And you can see here, the point of merger, which is akin to the centromere, is our actual answer here, our actual composition. This is acting as a genetic code. Now, let me get to. Okay, so back to the simplest space here. Now, this is three metal, and we plotted these three metals. Now, what happens when we have more and more metals? Then the dimensions increases, and we kind of plot this graph. In that case, what we do is we say, okay, if I put a ball at the top where you see gold, what would be the shadow that's being projected at the floor? That shadow is the projection. And with that projection, you would again see the same point of merger in these points. And this is a projection that we produce down here. You can see it's much easier to see, and you'd be able to do visual analysis of where the composition is. And this is exactly what you would find in, let's say, higher metal. We get to four metal system, and you would get very similar results here, where the triangle, which is the iso-pycnic region in this tetrahedron, that triangle will be projected down, so you would end up with a triangular projections, and in that you would also see this point of merger. At the very bottom, right here, this is the projection that we got for the triangle of them, right? Okay. So when we do this analysis for, let's say, 6 metals, with this projection graph, we can figure out what's so with this, we can figure out where the actual composition is. I'm going to keep this on hold for a little bit. I'm going to switch back to 4 metal program. This will compute in that time. So here. So for this one, this is 4 metal. We're going back. So when we plotted all these compositions against each other in this similar space, we found a very beautiful pattern here. These are fractals forming. This is seen in all metal programs, and these are its natural arrangement of all these compositions. And you can see there is no symmetry here. It's very, it's a pattern, but there is no symmetry here. But when I zoom in, I can see that there's one place where all 6 series compositions have the same value. And this is where we find symmetry. This is the only place where symmetry exists. So going back to here. So you can see with 6 metals, we only have the projection graph, and we have these beautiful fractals that are being produced right here. Okay. Now here, what I'm going to do is I'm going to quickly put in a particular density for 8 metal alloy system, and I'm going to leave it to run in the background. So to recap a little bit, let's take a little bit of a breather here. So what we did was from the bottom left corner, we had a composition that we didn't know of. We just had a density of it. We knew the metals, we knew the density. We fed this into a computer that I just showed. This math mill produced all these different possible compositions there. All the series are produced. This is our data, the real-time data that is produced. In that, it put into a fractal. It analyzed all the data, and it found that point of symmetry, that merger, point of merger. And from that, we found the actual true composition here. Now, that entire data that goes into a whole host of other things. It can be classified into how many ternaries are possible, quaternaries are there, and so on and so forth. So this is the list for 3 metals for this particular alloy. And you can see all of these were created in real time in that length of an eye. And this data is very useful for a whole host of other things. You don't even know what it might be used for. So for this program, we have, so a 6-metal program can identify all the alloys from pure metal to binary, ternary, quaternary, senary, so on and so forth. So if you have a 6-metal program, you can figure out a quaternary alloy, no problem. It will tell all the others being 0, right? And with that being said, it automatically assumes the sensitive formula for 6 metals, and within this you can only use 2 series to figure out which is the composition. Now this does not interfere. The additional metals do not interfere with the alloy analysis. Like if we are trying to do quaternary, it's not, and you have 6-metal program, not a big deal. It's not going to affect the results. Okay, so what we propose is the alloys need to be classified in 2 different categories: binaries, which have only single compositions, and then we have non-binary alloys that have multitude of compositions possible. In this case, so we say ternary, we have so many, as you can see, series of the isodensity compositions. How many possibilities are there? Calculator probable values and number of PICs. As you can see, the number increases very, very rapidly. So the higher metal program you go to, the more difficult it becomes to compute. And the more computation power you need, the more storage space you need to store all those series together. So here is a quick graph. And on the left, you can see when we change the number of metals from 3 to 4 to 5 to 6, so on and so forth, what happens, the number of compositions. And you can see it's an exponential problem at the very top. But we remove all the negative values, we can optimize it further, and we can get it into polynomial number of compositions, that kind of thing. On the other hand, if we change the degree of discretization, where initially I mentioned we have 0, then we plug in 1, 2, 3, 4. Instead of that, what we can also do is plug in 0 and then 0.1, 0.2, 0.3, 0.4, so on and so forth. So if you change that from 1 to 0.1 to 0.01, so on and so forth, you can see the complexity increases, the more computations are needed. Okay. So here's what happens when the number of metals are changed in the program. And as you can see, there is always the right metal here. 0% error here. And as you can see, the time for each, there's 3 metal forces, the time is included. And then when we change the iterative step, let's see I equals 1 to 0.01, the time is increasing rapidly. Now, when we change the accuracy, so that number that I fed for the density, when I make it more accurate, what happens? Or let's say for some reason my density measurement was not accurate. Well, in that case, you can see we plugged in each success. We increased the density and computed each and every answer that our software produces. And for all these different programs, you can see it is very, very chaotic in the beginning. The answer changes very, very rapidly, and it's almost unpredictable. But there reaches a point after which everything stagnates. And no matter how much you increase the accuracy, your answer will stay the same. So now when we thought about that, we also changed the density. We started increasing the density, decreasing the density. And we found out that when we did that, it produced something of this sort, where we have, as we are increasing the density, we have just these particular compositions that are being created, no more, no less, no in between. These are like pockets. If you have a density, it will fall into any one of these categories. So now, going back, with these pockets and with these stagnations that are happening here, we have a very interesting way of self-authentication where we cannot authenticate whether our answer is correct or not. We can compute it with one accuracy and then change the accuracy and see if we get the same result. And we would know for sure it is the correct one. As you can see, after a certain point, the composition became the same. So it is falling into one particular pocket. And after it reaches that particular accuracy, it will not fall out. And this is what we found when we changed the precision. We're noticing that same thing. Now, with these pockets, when we change the iterative step, we go from 1 to 0.1. Well, we see the pocket in the 1, it's very, very large. But within that, we have so many pockets present from 0.1. Important thing to note here, right here on the right, you can see the composition for the pocket, big pocket in 1, will also be present in one of the pockets in 0.1. Now, going back. So we have living matter, non-living matter. With the living matter, we have perfect way of identification, the density being the genetic material. And we can create the genome. And from that, we can figure out all the different properties. Same thing we're able to do here. With density, we have so many different compositions being present. We have so many different ways we can authenticate whether it's the correct answer or not, so many different things. So we have the density genome, which is the iso-pycnic region, which tells us exactly what compositions are going to be there for that alloy. And then we have the entire space, the triangle, to be the pan-density genome, where all the possibilities out there are going to be in there. Okay, so starting from the Archimedes principle, Archimedes work, we had nuclear development in 2004, where we modified the Archimedes equation. This was the first time we worked on it. Nobody has ever worked in this field too much. And then from there, we have the introduction of softwares to be there to compute this composition. So now we have the graphical analysis and stuff of that sort. And then at the very end, we're able to do this on a website, and we're able to create real-time databases on websites. So that is one number right through here. So we have real-time data creation. We also have big data, which is already being worked on. So if we integrate these two together, we have a whole host of new fields to emerge. We have completely sustainable it would be very sustainable. We have smart manufacturing. We have green technology because it is being created on spot. There is no carbon footprint for the storage of data, and so on and so forth. So many possibilities are there. And then with the take-home message, ultimately we have you. If you can tell us the density and the constituent metals, create metals, we can tell you the compositions and the fingerprints. And you can contact me here. Before I conclude this, I would finish up with 8 metals. Here, it computed. So right here, you're seeing 8 metals: platinum, gold, silver, copper, cobalt, zinc, aluminum. It produced so many compositions here, and then it took 397 seconds, which is still a lot, but considering it is 8 metals, this is feasible, and it is being done on a regular computer. Okay. All right. So at the end, I would like to thank UPenn for having me here. And I would definitely want to have special thanks to everybody present here and people who helped me with this event and getting it to reality. Without you guys, it would not have been possible. So I'm very, very thankful for making this happen. And Anvilworks, who provided us a free of cost platform for just this research work to develop our website. And again, thank you so much. If you have any questions, I'll be ready to answer. Thank you.
Thank you very much, Jay. Let me just mute you so that we don't have. Yes, thank you. It's wow, a lot of work. Very sad that your mom is not here to enjoy this presentation, but I can tell you that your work mom is very proud of you. Thank you for sharing it with us. We can open the floor to questions. My understanding is that other members of the research team are online. So if anyone has questions, please ask them on the chat. I will start with one. Did you say that this platform is publicly available online? No, you're muted.
Yeah. So when it comes to whether this platform is available publicly online, not right now, but we are planning to have this publicly online for public use after all the publications and everything is set. But we are planning on having this available to general public.
Jay, hello. Can you hear me? Yeah.
We do have a question.
Yeah.
Go ahead, Doctor. No, we cannot hear. Why can't we hear? Let me. Let's try this. Can you go ahead?
So, can you hear me?
Yes, now we can hear you. Yes.
Yeah. Congratulations, Jay, for a wonderful work. In fact, I had many questions in the middle of your presentation, because I was thinking that what if there is a very thick layer of the adulteration, if there is a thin layer of the adulteration in a specific antique or a metal. But you have almost solved the queries because according to the different type of matrix, you can also identify that, where there is a different type of alloy or metal combination. So my only curiosity is that if you can work on the similar kind of thing, if where other kind of things like in the eatable or drinkable, if there is a kind of the adulteration where metal is involved, if your expertise is metal, then like there are so many other things where the density may work, like in case of the, especially like a big racket on the liquor, like single malt whiskey. So there are the bootleggers who are producing. So if you can, like, because it's not possible to open the bottle and check and then you say that no, it's not. it's not good. So in that case, and you know, that is a very big business because things are very expensive, you know. So similarly, there are also like milk or dairy products, and how you can like explain that if similar kind of the technology can be used, density theory, to predict or to diagnose if things are okay.
Hi, sorry. I'm getting the reverberations. All right. So to answer your question, thank you for all the suggestions. And yes, density for other compounds, we also considered that. So if you think about the triangle graph that we had, instead of gold, silver, copper, or in four metal tetrahedral, instead of gold, silver, copper, zinc, if you put in carbon, nitrogen, oxygen, and hydrogen, if you think about it, just to think about it, all the possible molecules, the hydrocarbons comprised of these four elements will be present in that space somewhere, right? Because it is taken in percent, now all the empirical formulas in chemistry would no longer be applicable, but in percent, it would still be present on this graph, right? So with that, if we have a way of defining how, just like in alloys, we were able to define the density, we can figure out, okay, with density, we have a region that is produced within this graph, and from there we can do the analysis. So if you can figure out a similar definition for these compounds, for just in case all these hydrocarbons, then we would have a very, very novel way of identifying the compounds. And it also goes further to whole hosts of other materials, whether it's liquids, whether it's solids, other different things. So that's a very, very, very important topic that we need to consider. And thank you for suggesting that.
Great, thank you.
We have one question on chat. Jay, are you able to read it, or should I read it for you? You get it? Okay. Why don't you read it for everyone in the room as well? Okay.
Oh, no. Oh, no. Sorry about that. Okay. We good? All right. So, sorry about that. I was muted. So this is a question from Chandan Rao. Thank you for all the comrades. So the question was about the trace metals present in an alloy that would give the wrong analysis because it is present in such small quantities. And for that, our density method will definitely work in that case because we can do n metals first and foremost. And then second, if it is trace metal, we can increase the degree of discretization. We can go for 0.1 instead of 1. And you would be able to figure out whatever trace amount it is. It's just that with trace metals, you would need more computation power. I hope that answers the question.
Jay, actually, the presentation was the self-explanatory. So I think that's why there is no need for the further questions because everything was well explained, and so I think there is no need for the further question.
Thank you. Thank you.
Okay, thank you all. Thank you all again for attending, and let's give it for Jay one more time and for family.
Yeah.
Have a good rest of your day, everyone. Let me stop recording.